Okay, so the next step here is to make some connection between mass and moles. And mass is what we normally measure things in the lab. We can also use volume, but we'll start out with mass, and we can just put things on a scale and get a certain amount of it. There is a way to connect how much mass you're taking and how many moles, or in other words, how many particles of a substance you're taking. So that's what we're going to look at now. We could try counting, just counting the particles, but there isn't really a way to do that. They're too small for us to count. We can't physically see them. And if you actually added it up, like here's a little analogy, it would take you over 19 million years to spend Avogadro's number of dollars. So remember that's 6.02 times 10 to the 23rd dollars. 6.02 times 10 to the 23rd dollars. If you were given that, it would take you 19 million years to spend it. And that's spending at a rate of $1 billion a second. So just thinking of that, being able to even count to a mole, which would only be a teaspoon of water, and you needed to get a whole liter of water, being able to count that would be impossible. The number of years and time it would take, even if we could count particles, would just be ridiculous and absurd. So what there is there's a relationship between mass and moles that we can use in order to get out a certain number of molecules. Okay, it's kind of like if I told you to get if I gave you like a jar, and inside that jar were a bunch of jelly beans, and I told you, asked you to count up how many jelly beans there were in the jar, but you couldn't actually take the jelly beans out. They were kind of in the jar, and you weren't allowed to take them out. But you knew at least one thing. You knew how much a jelly bean had in terms of mass. So if you knew that, I think most of you could probably calculate how many jelly beans are in the jar. So if we knew that one jelly bean had a mass of 1.5 grams, and we know that the jar of jelly beans, let's make it easy, say it had a mass, say there was a mass of 15 grams of jelly beans in there, most of us could see that, okay, we take the 15 grams and we divide it by the 1.5 that goes for each jelly bean, and we get a total of 10. So that's what we're talking about doing, being able to use numbers to calculate out moles and to count things, like we just counted the jelly beans, but doing it from mass, because we can easily and quickly measure masses of substances where we can't, it would take a long time. Even with the jelly beans, let's say there was 500 jelly beans in the jar, to count them out would take a long time if I wanted you to go and get 430 of them. But you could figure out the mass of 430 jelly beans and just dump them on the scale. Okay? So that's where we're headed. So the first thing we got to do is get this relationship. Let's say that was true for jelly beans. One jelly bean is 1.5 grams. What's the relationship for atoms and molecules? How are atoms and molecules connected to mass? So that's where these next two pieces of information come in. Okay, so the first one is called molar mass. And what molar mass is, it's the mass of 1 mole of any substance. So let's start out with just examples of elements. It would be 1 mole, or 6.02 times 10 to the 23rd atoms of an element would have a molar mass, whatever that happens to be. And it's different for every element. But luckily we have the periodic table. And on the periodic table, that information is already there for us. Because for an element, the molar mass is equal to the atomic mass. So molar mass and atomic mass, they can be set equal to each other. The atomic mass tells you how much one atom weighs. So for instance, if we had an atom of hydrogen, it would have a mass of 1.01 atomic mass units. And atomic mass units are just tiny little units that we use to measure the mass of an atom. But if we had a mole of hydrogen, so we had a whole mole of hydrogen atoms, then what we do is take the same number, 1.01, and we change the unit from AMUs to grams. So the molar mass of hydrogen is 1.01 grams per mole. And you can go right to a periodic table and get that information. And so you don't have to look anywhere else. All that information is already on the table and easy to find. We just need to know that this relationship is true, that if you take a mole of any atom, its mass is going to be equal to its atomic mass. Just switch it into grams. Okay? So let's take a look at a couple of examples here. Okay, so these examples here, we've got gold, magnesium, and oxygen. So to look these up, it's fairly simple. We just go to a periodic table. So I'll just grab my online periodic table here. And we find the element gold, which is right here, element number 79. On this one, I have to click to get the information. And then we get the information here. Atomic mass is 196.9. I'm just going to go to 2 decimals. 196.97. Okay, so 196. 196.97. Now that would be for an atom, that would be atomic mass units. But for a mole of those atoms, it would be grams per mole. Okay, so all the data is there. We're not learning anything new. We're just using those numbers in a different way. Now we know that if we take 197 grams of gold, we're going to have 6.02 times 10 to the 23rd atoms of gold. That's our new relationship that we can work with, and that's going to let us put things on a scale, mass it out, and figure out how many we have. And let's take another look at another one, magnesium. So again, if we go to our periodic table, magnesium is over here in the second group, and its atomic mass is 24.31. Again, I'm just rounding off to 2 because I think your table that you have at home probably rounds things off to 2. So 24.31 grams per mole. Okay, and same thing. That's 6.02 times 10 to the 23rd atoms of magnesium, would have a mass of 24.31. So they're the same number of particles, but they have different masses because those particles are different sizes, of course, right? Gold is an atom that has, let's just go back, take a look at it quickly here. Gold is an atom here, you can see it, number 79, so it has 79 protons, it has 79 electrons, it has close to 80 neutrons. It's a much bigger atom, so if you have a mole of those, they're going to weigh much more than a mole of magnesium, which only has 12 protons and 12 electrons and 12 neutrons. So the size of the particle affects what the mass of the mole is. And we see that in this last example. Let's just take a look at oxygen. And so oxygen is 15.9994. So normally I just round that off again to 2 decimals. And I often write oxygen as 16. You can certainly be more precise if you want, but most tables I look at, they usually do it to 2 decimals. So 16 grams per mole. So if we went to the scale and we're able to get 16 grams of oxygen, we would know that we have 6.02 times 10 to the 23rd atoms of oxygen. Okay? And that's all there is to molar mass, just knowing where to get the information and how to look it up. So we'll give you some practice on that in the worksheet, but let's take this one step further, and then that'll be where we'll stop today. So in terms of molar mass, this is great if you can do it for elements, but what about for compounds? So the molar mass of a compound, or a formula unit, which would be an ionic compound. So the molecule or the formula unit is found by adding up the masses of all the individual atoms that are in the molecule. So it's just a matter of using the formulas that we've been learning to write and name, and then use those to figure out how many of each kind of atom is in a molecule, and then add up the masses of all those individual molecule atoms in there, and we would know the mass of the molecule. Okay. So for instance, if we took water We'll do this a little bit formally for the first one. Eventually, you'll probably just do this as a little side calculation. But for now, let's do one formally here so we have the process. So we look at water, and we want to know its, sorry, I should say its molar mass. It has 2 hydrogen atoms and 1 oxygen atom. So hydrogen, if you look it up on the periodic table, it's 2, and its mass for hydrogen atom is 1.01 grams per mole. And the oxygen, we talked about that on the last screen, is 1 of those for 16 grams per mole. And so the total here, if we add this all together, is a mole of water molecules would have a mass of 18.02 grams per mole. So if I gave you 18 grams of water, you would have 6.02 times 10 to the 23rd molecules of water. Okay? So it's not that much. You just have to be very careful that you have the right formula and that you carefully add up all the parts. But if you do that, you can get the mass of 1 mole of a molecule. And now that really starts to help us when we do lab work. Okay? Let's take a look at another one here. Let's use sodium sulfate for our next example. So I'll pause for a minute, and you might want to stop the video, try and figure out the mass of molar mass, the mass of 1 mole of sodium sulfate, and then we'll get back together and we'll check our answer. Okay, let's take a look at the answer. So if we, again, I'm just going to write this one out formally. So there's 2 sodiums plus just 1 sulfur plus 4 oxygens. So that gives us what's in this compound. And so sodium, so it's 2 times, oh, I'm sorry, I've forgotten sodium. I'm going to have to look it up. I think it's 23 something. The mass of sodium is, 22.99. So sodium is 22.99 grams per mole plus 1 sulfur. The sulfur is 32.06 grams per mole plus 4 oxygens at 16 grams per mole. Okay, and if we add that all up and use our calculator, and we get a total of 142.04. So 142.04 grams in a mole of sodium sulfate. Okay, so that's the next little piece we've got to learn, how to calculate both molar mass in an element and in a molecule or a compound. And then we can move on from there, but we'll stop there. I'll give you one more example. I think, what have I got yet? One more example. Let's try this one, Al2O3. So again, pause your video, give it a try, and then come back and check your answer. Okay, and let's give this a try. So again, we can write this one out. So the molar mass would equal, we would have to have 2 aluminums plus this time 3 oxygens. And again, so we go 2 times, need to look up what aluminum is. Let me flip over to my periodic table. And aluminum is 26.98. grams per mole. And then oxygen, again, some of these you just start to memorize. 3 times 16 grams per mole. And again, if we go to the calculator and add that all up, we get 101.96. So 101.96 1.96 grams per mole. Okay, so I'll post a worksheet that has a few more of these on it and some of the answers to the questions from the textbook. I think I have that down as Wednesday's activity to get done. And if you have any questions, please just put it in the comments and we can come back and explain it a little bit more. Okay, we'll leave it there for now. Thanks.